Hi, this is Dr. Winters, and this lecture video is intended to cover the topic of colligative properties, specifically focusing in on a conceptual understanding of them and providing a couple of equations that we can use to calculate values mathematically surrounding colligative properties. There will be another video that covers the use of these equations for doing these types of computations. So let's take a look at the colligative properties. Well, a good place to start is by defining colligative properties and listing them. And as it turns out, these are properties that depend on the amount of dissolved solute, but not on the identity of the dissolved solute. So we want to know how much sugar is dissolved in the water, or how much salt is dissolved in the water. And the things that are changed as a result of this solute being dissolved into a solvent are the freezing point, the boiling point, the vapor pressure, and osmosis or osmotic pressure. So these four different properties vary, and hopefully we'll come to see that vapor pressure really has a profound influence on the boiling point and is really integral here in our colligative properties. So it's handy for us to begin by just considering the way that a non-electrolyte, non-ionic solute dissolves, because they don't dissociate. So a good example here would be something like sugar, where when we add this into water, it dissolves, and the number of sugar molecules that we started with equals the number of species that are dissolved in solution. As it turns out, Raoult's law says that the vapor pressure of a solution with a solid or non-volatile solute decreases from the pure solvent, meaning that the vapor pressure of water, pure in this case, is going to be greater than the vapor pressure of salt water or sugar water. Okay, well, that doesn't give us a mathematical handle on it, but it at least explains what we should experience or what the types of values we should expect. The reason for this change in vapor pressure is because we see that the solute molecules have solute-solvent interactions that we've talked about previously. These interactions in solution cause the solvent molecules to be bound more tightly into solution than they are in the pure liquid, in that pure solvent, and therefore less of them escape into the vapor phase above the solution. So we expect to have a decrease in vapor pressure. This is going to in turn affect boiling point, since the boiling point of a liquid, whether it be a pure liquid or a solution, is equal to the point at which the vapor pressure inside the liquid equals the vapor pressure outside of the liquid, and that's when we start to see bubbles forming spontaneously within the liquid. All right, so let's take a little closer look at an equation here. The vapor pressure then of a solution, that's the P1 on the left, is going to be equal to the mole fraction of the solvent. So out of 100% of the number of atoms of chemical species in solution, including the solvent and the solute or solutes, how much of that, what fraction of it, is the solvent, that's X1, times the normal vapor pressure of that solvent. That's why we have the standard symbol. So the standard vapor pressure there for P1. So this is a mathematical way that we can handle it. We need to be able to handle mole fraction and we need to be able to handle pressures, but it's a simple equation aside from that. So now the question is, what sorts of experiences do you have that support this law, that vapor pressure is different? Well, as I already said, the boiling point, it happens when we experience the boiling point happens when the internal vapor pressure equals the external atmospheric pressure, and so bubbles start to spontaneously form. And so we do have experience with this in that we add salt into water to increase the boiling point. You may notice in some recipes that you've followed when you're cooking or baking that it may say to boil noodles longer at higher altitude, or to add more salt to the water to increase the boiling point. So these all play into the same understanding in a molecular level of the solvent interacting with itself and the solvent interacting with the solute molecules in solution. All right, so let's cross out this top part and move on Here we have the vapor pressure of the solution then, as we said already, as a review, is equal to the vapor pressure of the solvent times the mole fraction of the solvent. Another way to write this, because we know that X, the mole fraction of the solvent, is going to be equal to 1 minus the mole fraction of the solute. This is an important understanding for us because it's a way that we can substitute in the mole fraction of the solute in particular cases where it might be easier to calculate, or maybe that's a value that we're given. Okay, so now we briefly discussed that covalent or molecular species like sugar don't dissociate when they're dissolved in water, where ionic compounds or electrolytes do. They form these ions. So in the example of something like sodium chloride, we know that we start with NaCl in this crystalline lattice, and as it's dissolved, we end up with sodium cations and chloride anions in solution. Well, as it turns out, not all electrolytes dissolve or dissociate equally, and so we have this value we call the Van Hoff factor, and it's given the lowercase letter I. It's equal to the number of moles of particles in solution versus the moles of solute particles that were dissolved, that were placed into the reaction. And so it's just a fraction that allows us to understand how much of our electrolyte is actually dissociated. So for sodium chloride, as an example, since we're talking about this, a solution that is 0.05 molal, so remember this is molality, the moles per kilogram of solvent, I is equal to 1.9. Well, what does this mean? It means that we have 1.9 moles of particles that come from 1 mole of sodium chloride. Remember that, as I said, sodium chloride breaks up into Na plus and Cl minus, so if we put in 1 mole of sodium chloride, we expect 2 moles of particles, of ions. But we only get 1.9. It's less than complete dissociation, but it's nearly complete. This is considered a strong electrolyte, and for most cases we consider this to have complete dissociation, though we see here as we evaluate more thoroughly the Van Hoff factor, it's not complete. It's actually about 95% dissociation. Okay? So the Van Hoff factor is going to be useful for us as we start to try to figure out the mole fraction. We may need to use a Van Hoff factor to figure out actually the number of moles of a species present in solution from the moles that we thought we put in there before we can calculate something like the vapor pressure of a solution. Let's take a look back then at Dalton's law. So remember that Dalton's law says that the total pressure of a system of gases is equal to the sum of each of the individual gases of the pressures. So P total is equal to, for example, PA plus PB. Okay? Well, Raoult's law only applies to non-volatile solutes, which means these are solutes that do not vaporize easily. So as predicted by Dalton's law, the overall pressure of a mixture of volatile liquids is going to be equal to the sum of the vapor pressures of each of the individual liquids. But it's not exactly, we need to treat it a little bit more carefully as we're mixing these liquids, because each one of them does not contribute its complete vapor pressure. They're scaled by their mole fraction. So when we make a solution, let's say we mix together benzene and toluene, two organic molecules that you likely have heard of before. Benzene, of course, being a 6-membered carbon ring with alternating double bonds, and toluene being the same type of ring with a methyl group off of one position. We see that the total pressure of a system like this is equal to the mole fraction of benzene times its normal vapor pressure, plus the mole fraction of toluene times its normal vapor pressure. The problem we would have if we did not scale with the mole fractions is that we would have a cumulative effect of both pressures. And so just by adding in 2 or 3 or 4 different volatile solvents, we'd be able to increase the overall vapor pressure significantly. What this does is it scales it so that you end up with an averaging effect based on the amount of each that has been added into that mixture or that solution. Okay, so this is going to be an important equation for us to work with going forward also. So let's take now another look here. We of course have this list of colligative properties, boiling point elevation and freezing point depression being among them. Let's take a look at these a little bit closer. Since the vapor pressure of a solution decreases when the solute is non-volatile, we then expect that the change in the boiling point is going to be equal to some constant. The molal boiling point elevation constant is what we call it. This is a value that will be given to you, times the molality. Okay? All right, so let's take a look at this plot here of pressure versus temperature. Of course, this is a phase diagram where we can label solids, liquids, gases on it. And already in this lecture video, we've said that the vapor pressure is going to go down when we place a non-volatile solute in our solution. And so if we draw this out where the blue curves represent the solution once you've added the solute, and the orange curves represent the original pure solvent, of course we see pressure on the y-axis, which is why the blue curve is drawn at lower pressure. And then we also note here that when we see the crossover point, or the intersection between the curves, we can solve for various temperatures and pressures. So, for example, we know that the boiling point will only happen once the internal vapor pressure reaches the external atmospheric pressure. So I've drawn a dashed line from the pressure axis across all the way over to the right side. That's a horizontal line parallel to the x-axis because it's a constant pressure in the atmosphere. So we're looking for the point at which that dashed line intersects the orange curve and then the blue curve. Then we draw vertical lines down to the temperature axis, and that indicates the two different temperatures. From the orange curve, we see the temperature at which the pure liquid would have boiled. And then for the blue curve, we see the temperature for which the solution will boil. And what you'll note is that the solution will always boil at a higher temperature. Similarly, we can do the same sort of analysis with the solid to liquid transition. We have a blue line drawn in. We've drawn dashed lines from the point at which those intersections happen. And what you'll note is that we always see a decrease in the temperature for the solution, the freezing point of the solution. So we see boiling point elevation and freezing point depression. This is, again, why we add salt to water when we're cooking, and as we'll see, there's a good reason, a good way that we can leverage the freezing point depression for all kinds of other things. We'll talk about that in a moment. Okay, so the last property that we had listed was the osmosis or osmotic pressure. So some different types of membranes, you can think of these as like a plastic type sheet. A good example of a membrane actually is the walls of our intestines. And so these are semi-permeable membranes allowing nutrients to absorb through them, to travel through them, but not allowing everything to travel through them. So some membranes are semi-permeable, allowing water and other small molecules to pass through the membrane. And osmosis relies on this because it's the movement of water from high concentration to low concentration through one of these membranes. So what we see here is on the left we've drawn pure water. On the right we're drawing salt solution with some ions. In between, the dashed line represents the semi-permeable membrane. We then see, based on what we understand about osmosis, that it's the movement of water from high concentration to low concentration. Of course, the higher concentration is in the more pure water. So those water molecules, by the rule of osmosis, are going to travel from left to right in our diagram, reducing the concentration of the salt on the right-hand side and changing the volume of pure water on the left-hand side. Well, associated with this change in volume is that we see the membrane pushing back over time. So eventually pressure builds up on the right-hand side, and it causes water to move at equal rates from left to right and from right to left. Because as one water molecule might move in to the right-hand side via osmosis, that might cause the pressure of the membrane to increase sufficiently to push one water molecule back to the left. So we reach an equilibrium point at which those rates are equal to one another, but in opposite direction. And this is the image of osmosis that we use, the conceptual idea of it. But osmotic pressure then pi is equal to the concentration of the salt times the gas constant times the temperature in Kelvin. Again, simple equations for colligative properties, equations that we'll take a look at solving and using for computations in another video. The point here is that they're not difficult equations, but we will need to know how to implement them. So I want you to keep track of that and to work some example problems. So to close out here, I'd like to give you a couple of examples of how colligative properties are leveraged. First of all, we use them for melting ice on roads in the winter. We can use colligative properties for making ice cream to sort of super chill the cream. We can use reverse osmosis to purify water. We'll be able to determine the molecular mass of a compound in the laboratory this semester using colligative properties. As I mentioned also, we can leverage this to increase the boiling point of water. If we're cooking noodles in Denver, for example, the boiling point would be reduced, the noodles wouldn't cook quick enough. We might add a little bit of salt to try and help increase that boiling point. So these are some useful applications of colligative properties, along with some equations, some conceptual understandings, and the actual computations will follow.